This is a video presentation of mechanic of machines for final project, which is titled All Pump Jack and prepared for Dr. Mhadi. And these are the team members: Shah Adam Stephen, Ahmad Azeem, Richard Owens, Haziq Bukhari, Mohammad Hafeez, and also Mohammad Hasseb.
Assalamu alaikum, I'm Mohammad Azeem, and this is the abstract part of the project. The rod lift pump, also known as the oil jack pump, is widely used device for extracting fluids from underground wells. The project main focus is on designing and analyzing a 4-bar linkage system for this pump. The analysis include the configuration diagram, velocity analysis, acceleration analysis, and also the force analysis. The primary objective of this project is to achieve an optimal pump speed for the efficient delivery of the fluid, to enhance the system efficiency for the stroke length and speed control. The methodologies use a systematic approach for the mechanism synthesis and analysis, utilizing advanced computer-aided design softwares. Also, the equations of the motion statics are applied for the calculations of the performance, force, and torque. The study aims to improve the oil jack pump durability and lifespan, leading to reduced maintenance and increased safety. And lastly, it is to optimize the pump speed and operation helps minimize wear, contributing to cost saving and a safer working environment during maintenance
The
and
rod
maintenance.
lift pump is a widely used device for extracting fluids from underground wells. It operates using a series of steel rods connected to a pump at the well's bottom. A surface-mounted power source creates a reciprocating motion, drawing fluid up to the well for efficient extraction. Ideal for low production wells, the pump's 4-bar linkage system optimizes stroke length and speed to enhance efficiency, particularly in deep well fields.
So, the methodology for the mechanism design of oil pump jack involved a systematic approach to create an efficient and reliable pumping system. Here are some of typical methodology that I have included here. Okay, first thing first is requirement gathering. Understand the specific requirement and operational parameters of the oil pump jack. These include factors like oil well depth, production rate, stroke length, power source availability, and any environmental constraints. And the second one is conceptual design. Develop initial conceptual design for the oil pump jack mechanism. Explore different configuration and mechanism that can efficiently convert rotational motion into reciprocating motion to drive the pump. And the third one is kinematic analysis. Perform kinematic analysis of the selected mechanism option. Use mathematical models to determine the relationship between different moving parts, velocity, acceleration, and position. And the fourth one is dynamic acceleration. Dynamic acceleration is a conduct dynamic analysis to evaluate the force, torques, and stress experienced by different components during operation. This analysis ensures that mechanism can withstand the loads and forces encountered during pumping without failure. And the second last one is CAD modeling. Created detailed computer-aided design models of the selected mechanism. CAD software enable precise modeling and visualization of pump jack, facilitating design, modification, and optimization. And the last one is optimization. Continuously iterate on the design, incorporating feedback from simulation and testing to optimize performance of the pumping jet mechanism. This step aims to improve efficiency, reduce wear and tear, and enhance reliability. Throughout this methodology, collaboration between mechanical engineering and expert and all industry professional is essential to achieve a successful and efficient oil pump jet design. That's all from me.
For the velocity analysis, we take this diagram with the 4-bar linkage system. So we divide this diagram into two parts as it should be. The first one, diagram 1 is A, B, C, D, and the second diagram is D, E, F, G. So for the first angular velocity, we have the given value which we convert into radian, which becomes 0.42 radians per second. So by calculating, we get the values for the first diagram as VAP for 0.84, VCP to 0.9, and VDC to 0.75. From diagram 2, we get this value for VDE is equal to 0.5, velocity of EF is equal to 0.65, and velocity of GF to 1.3 meter per second. By using these, we get the omega 1 value, which was the given value at first, and then we get the omega 2 value, angular velocity, sorry, 2 value, which comes out to be 0.15 radian
So
per
this is
second.
the results for acceleration analysis. When we are assuming constant velocity at link CE, we can actually find acceleration at link DE, EF, and also the slider. So the main objective here is to find the acceleration value for link EF, which is when we calculate, we obtain 0.0267 meter per second square. We will need to find the acceleration value for EF because it is attached to the cylinder rod. This cylinder rod is the value of acceleration of EF is needed for the force analysis.
For force analysis, we have five forces acting on the sixth link. The weight for link is obtained from the mass of the link and the gravitational force. For inertial force, which is equal to ma, the acceleration is obtained from the acceleration analysis from the previous slide. For the frictional force, which is equal to mu n, we are assuming the value of mu is 0.8 for the contact point of link 6 and the wall. After that, we have normal force acting to the right horizontally. And lastly, we have force 65, which is acting 40-degree counterclockwise from the y-axis. The normal force and force 65 are obtained from both y and x component force equilibrium equation. For link 5, there is only two forces acting oppositely towards each other. By third law of Newton, these two forces will have the same value, which are 39,069 and 6.
Continuing from my group mate, at link 4, we can get the force at F for 5 using the calculated force from link 6, which was 39,096.6 Newton with the angle of 50. Since the force is moving opposite from F54, we input the force as negative 39,096.6 Newton cos 50 degrees, and we get the F for 5 equals to 25,130.81, which then we can use to get F34 at link 3 with 25,130.81 Newton cos 59 degrees, which is equals to 12,943.32 Newton. We can also get F32, which is simply negative F34 equals to negative 12,943.32 Newton. Finally, after getting F23, we can find the torque to 1, where T to 1 is minus F23 sine 40 and times with 2, which is equals to 0. We calculated T to 1 and get 16,639.61 Newton meter.
Next, discussion. So our design for this project is based on the API C series beam pumping unit. So this is the most utilized design for ground power equipment and road pumping operation. The operation has multiple challenges, including ineffectiveness and time consuming, high maintenance costs, and the possibility of injury due to the fluid's toxicity. So it is possible to avoid inefficiency and waste time by determining the optimal pump speed. So to avoid this, several factors need to be implemented, including the implementation of advanced control system and automation technologies. This must be considered to achieve the optimal pump speed. So to accomplish this, the stroke length must be adjusted. The length of stroke should be adjusted to make it easier for fluid to move efficiently while avoiding stress on the system. Next, high system efficiency and flexibility are important in optimizing the pump jack mechanism's performance. High system efficiency can be achieved by improving the pumping process by adjusting stroke length and speed. High pumping efficiency can be maintained when the pump is filled with fluid on each pump stroke. Then, to achieve great mechanical efficiency, the prime mover need to generate adequate torque to manage the mechanical loads. So based on our calculation, the prime mover will generate 16,639.61 Nm torque. By having this torque, it can be ensured that the pump jack will have the power to overcome mechanical resistance and can move the pumping unit easily. This will enable the pump jack to efficiently extract oil from the well. Other than that, the length of the coupler and rocker can also affect the efficiency and performance of the pump jack. The most appropriate length for the coupler and rocker will help to optimize the pump's performance and enhance its overall efficiency.
So this is the last part of the discussion, which is to increase the optimization of mechanism to lessen human contact with fluids. When we are talking about optimization of mechanism, it is regarding the maintenance and inspection of the sucker rod pump. So based on objective 1 and 2, we wanted to produce a sucker rod pump that is more durable and has a longer lifespan without having to change equipment or do maintenance regularly. Thus, this can be achieved by producing a high-efficiency sucker pump mechanism that operates the pump within the calculated speed. This calculated speed can be seen in the velocity, acceleration, and also force analysis. Plus, this can also reduce wear due to a longer operational time and reduce the cost maintenance.
So finally, this is the conclusion. In conclusion, I would say with the objectives of achieving optimal pump speed, enhancing system efficiency, and minimizing human contact with potential hazardous fluid during maintenance and operation, the methodology used for this project was employing a systematic approach and advanced computer-aided design software. The project evaluated various linkage configuration using the CAD software to determine the most suitable design for the oil jack pump. Now the results. The study highlighted the importance of optimizing pump speed to meet production targets with overloading the system. The adjustment of stroke length and appropriate lengths of the coupler and rocker were identified as crucial factors in achieving this optimization. System efficiency and flexibility were emphasized to increase pump efficiency. The significance. The significance of this project extending this to the oil jack pump lifespan through a durable and efficient mechanism reduced wear, leading to prolonged operation time and cost saving. Targeted maintenance intervals also reduce human contact with the mechanism, which benefited the oil extraction. Thank you.